Welcome to the lecture for Chapter 1.1 of your algebra book. And today what we want to do is we want to become familiar with numbers in general. What are numbers? How do we categorize numbers? How many categories of numbers are there? And when we have a number, what are its properties? So to begin this journey, what we're going to do is we're going to start by looking at the very first numbers you were ever familiar with, and these are the counting numbers. They start at 1 and they go on infinitely. When we were first young, of course, we thought that they ended at 10, and there's a reason for that. There's a reason why we start at 1 and we count to 10, and that reason is quite simply because we have two hands, and on those two hands we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 fingers. These numbers starting at 1 and going on infinitely, but our first familiarity with them go to 10. These numbers are called the natural numbers. That's our first category of number, right? So if we think of a number like 37, well, that's a natural number because it is a whole number. Well, we'll talk about what whole numbers are in just a minute. But it's a number that if we were to start counting on our fingers with 1, our first finger here, and go all the way across to 10, and then come back over to our other hand again and go back to 11, and go all the way to 20, and so on and so forth. Eventually, we would land on 37. Now, it's helpful then to take a look at the way that the number 37 is constructed. We have what's called place value. And the 7 in this case, let's do that in another color. The 7 in this case is in the units place, or the ones place, meaning I can count everything from 1 all the way up to 9, and it will be right here, right in the units place, or the ones place. By contrast, the 3, this number here, is in the tens place. Once I get to 9, I need a new set of numbers, right? 9 is the most that I can count using only one digit. Now that I get to 10, notice that I now have a second digit. I'm using 2 digits now, so the second number is in the tens place. And these go by powers of 10, right? Each time I make a jump from one place to the next, I'm going by 10. So 10 times 10 is 100, so the next place would be the hundreds place. 100 times 10 is 1,000, so the next place would be the thousands place, and so on and so forth, right? And this we can do infinitely. Those are the natural numbers. Well, in order to achieve this here, in order to be able to write out numbers the way we do, we have to add a second concept, and that concept is the concept of 0. So once we add 0 to our list of natural numbers, we're now dealing with a whole other set, no pun intended, a whole other set of numbers called the whole numbers. The whole numbers are simply the natural numbers. Oops, let me undo that one. The natural numbers plus 0. And these are whole numbers. So in order to be able to write this 10 here, the way that we write it, our whole concept of place value, we need the concept of 0 in order to do that. At the number 10, I have 0 ones. 10 means I have 0 ones and 1 10, or 10 plus 0, and so on and so forth. So those are whole numbers. Next come a very interesting set of numbers. When we transfer over, now, so when we start counting, we're always counting up, right? But at some point we figured out, well, not only can we count up, but we can count backwards as well. So I have the number 1 here. And sorry about that, that keeps happening. Let's close that off. There we go. I have the number 1 here. And at the number 1, I am 1 away from this 0, right? 1 unit away from the 0. But I can also go 1 away from 0 in a different direction. I can go in a negative direction, and that will put me here at a negative 1. Same thing with a negative 6, right? Negative 6 is going in the left direction from 0 6 times. And that leads us to another concept we'll describe in just a second, whereas going in the right direction 6 times from 0, I land on a positive 6. So this set of numbers, these are called integers. And integers are whole numbers and their opposites. Remember, whole numbers include 0 and go on infinitely in a positive direction. Integers not only go on in the positive direction, but they also go from 0 to the left of 0 in a negative direction, also to a negative infinity. Well, let's stay consistent with our color here. They go to a negative infinity in the negative direction and to a infinity in the positive direction. Now this concept here I want to take a moment just to talk about, and that's the concept of absolute value. And the concept of absolute value means this. The absolute value of any number is its distance from 0. See, here I went 6 in the negative direction. So the absolute value of negative 6 is equal to 6. It's just the distance it is from 0. So you'll notice from this that whether a number is negative or it's positive, if it's the same distance from 0, its absolute value is the same, and we use these vertical lines to denote absolute value. Let's continue our journey with numbers here. Now we take a look, let's look back real quick. We've looked at all these numbers here, but there's a very interesting thing happening between here, just between here and here alone, and also between all of these other numbers as well. But let's just look at from 0 to 1. See, we know we can go in a positive infinite direction, and we can go in a negative infinite direction, and both of those are representations of infinity. But even between the numbers themselves, there are infinite numbers. For instance, just between the numbers 0 and 1, if I cut that in half, then I have a distance here of 1/2 and a distance here of another half. 2 halves is another way of writing 1. And then I can split those in half, and again I have a quarter there, 2 quarters there, which is equal to 1/2. These two are equivalent, and we'll get to fractions in a later video. And 4 quarters again is another way of writing halves. And we can do that infinitely. We can continue to go cut these in half from 16ths to 32nds, from 32nds to 64ths, and so on. But we can also cut them. In thirds. We can cut them in fifths. We can cut them all kinds of different ways. These numbers that we represent, let's write it this way. These numbers, fractions, are called rational numbers. And a rational number is any number that can be written as a number over another number. A over B is a rational number. Any number over another number is said to be a rational number. So 3 over 7 is a rational number. Or negative 5 over 2 is a rational number. 1 and 1/2 is a rational number. And of course all the other numbers, 1, 2, negative 5, all of these are all rational numbers because they can all be written. The number 6 can be written as 6 over 1, so 6 is a rational number. Then there's another even more interesting set of numbers. And these numbers are not rational. For instance, the distance between 0 here and slightly more than 1, but not quite 2, this point here, is called the square root of 2. If I have a triangle with a side of one length here and a length here of 1, then its hypotenuse, which we'll learn when we talk about the Pythagorean theorem, the hypotenuse is equivalent to the square root of 2. Now the problem with the square root of 2 is there's no way that I can write a number over another number that will represent the square root of 2. This number, if I were to divide it, I would divide infinitely, and it would be something along the lines of, well, let's try it with a calculator. I'll take the number 2 and I will square root it, and it's 1.41423, so on and so forth. Notice that you don't find any pattern. You don't find any, this won't stop. It only stops here because it has to approximate. I don't have enough room on my screen, and it would be dividing forever before it stopped. So these numbers that can't be written, they can't be written as a number over another number. They are not a terminating decimal. These are called irrational numbers. Irrational numbers. And there's some that we're familiar with. Pi, for instance, is an irrational number. We normally approximate pi to be 3.14, but in actuality it's 3.1415928, and so on and so forth. I don't know. It continues on forever. Now all of these numbers together, the natural numbers, the integers, the rational numbers, and irrational numbers, what are being called here real algebraic, but they include the rational numbers include these what we're calling real algebraic numbers, numbers that we can discover using algebra, and other numbers called transcendental numbers. And we're not going to get into these definitions too much in this class. This is for a different kind of algebra class, but not for ours. These make up what are called the, let's do this in a new color, let's use this bright blue, the real numbers. And real numbers are everywhere. These are the numbers we use to understand the world through science, through finance, through everything. From natural numbers to integers to rational numbers to irrational numbers. Don't forget the whole numbers, which includes 0. Then those are real numbers. There are other numbers that are outside of this field here, outside of this group. If I were to try and take, say, the square root of -1, can't do that because it's not a real number. But that's a topic for another video. We're going to continue with this concept in the next video. We will use that time to look at numbers and categorize them by these definitions. So thank you for listening, and we'll see you in the next video.